Hello, everyone. And now we're going to compute the determinant of a 3 by 3. Again, I'm going to show it as a trick. It's slightly more annoying than a 2 by 2, but it's not a difficult computation. But it's very, very easy to make a mistake. So here, now we're starting with a 3 by 3 matrix where the entries are A, B, C, D, E, F, G, H, I, and I want to compute that determinant. That will be a number. So here all these letters are numbers inside or entries of the matrix. So the formula, here we go. Okay, so the formula for det A is the following. It's AEI plus BF G plus CDH minus CEG minus AFH minus BDI. And if you remember the formula by doing that, good luck in your life. It's not going to be very useful. So the trick here, I think that's the best trick if you're using that formula to compute a 3 by 3 is to actually use the following idea. So if you have a 3 by 3 matrix filled with numbers, what you should do is boom, okay, you rewrite the first two columns of that matrix next to that matrix. And the way you get back this formula is by drawing the following arrows. So here, the first arrow essentially goes down the first diagonal, the regular diagonal. So the AEI is this arrow right here. Boom. So that's A times E times I. And then it's plus BFJ, which is the second diagonal when you move by 1 unit. So that's my second arrow. And then plus CDH. And that's my last arrow. So these three arrows, I like to call them. So starting with the regular diagonal. So these three arrows are like my plus arrows. And you can see here that the first three term, AEI, BFJ, and CDH are just multiplying these three entries along those diagonal. And where are the others coming from? These minus terms. So the idea is you just draw these anti-diagonal. So you start at C and you draw this first anti-diagonal, the CEG. So let me just draw that arrow. So poof, that's my first arrow, my first anti-diagonal. And then I have my AFH. So that's my second anti. Come on, iPad. Okay, so here we go. So AFH. So that's my second arrow. That is my anti-diagonal. And then the last one, the BDI, is this arrow here. And I like to call these arrows the minus arrows. So in this case here, I drew them in red. And that's, to me, the best way to remember the formula. Of course, you have access to a formula. You can do whatever you want, but I think this is the best way to compute correctly these determinants. So here we go. We're going to do some example with concrete numbers. Okay, so just to show you how these computations are actually done. So my first example, let's compute the determinant of A, 1 minus 5, 4, 2 minus 3 minus 1, and minus 7, 0, 3. So the first thing that I do is I just rewrite the first two columns. So my first column is 1, 2, minus 7. And then the second, minus a low, minus 7. And then the second column is minus 5, minus 3, 0. So you just rewrite the first two column, the first two. If you write more, it's just a waste of time. And now I'm going to draw my plus diagonals and my minus diagonal. So here my first one, 1 times minus 3 times 3. Then it will be plus minus 5 times minus 1 times minus 7, and plus 4 times 2 times 0. If you are clever, as soon as your arrow meets 0, you don't need to write that term. But for a sense of completion, I'm going to write everything here. So 1, so I'm going to do it in green just to remember where they come from. So 1 times minus 3 times 3 plus, okay, so I just continue, second arrow. Just be careful with the signs here. minus 5 times minus 1 times minus 7. You don't really need to write the third term because it's going to be a 0, but just to show you where all the numbers are going, this is how I get my last term, 4 times 2 times 0. And then I just do this again in the other direction. So using these anti-diagonal, so it will be minus 4 times minus 3 times minus 7, minus 1 times minus 1 times 0. Of course, with the 0, I could skip it. Then minus 5 times minus 2 times 3. So again here, I'm just going to write those numbers under them. So now all these numbers are starting with a minus. So it's minus 4 times minus 3 times minus 7. So just be careful. Minus, you could skip the next one because it's a 1 times minus 1 times 0, which would be 0. And then minus 5 times 2 times 3. And if you actually do your computation, just take your time, make sure you compute them maybe separately, but this will all add up to minus 98. So make sure you do it on your own. Again, this is my trick. If you've seen other ways to compute 3 by 3 determinant, you will never be forced to use a specific method. That's my favorite way. When I don't have a formula, some people just like to write down the formula. But to me, even with the formula, that little arrow trick is the way to go. My next example is my infamous identity matrix. So what will be the determinant of a 3 by 3 identity matrix? For those who know, when your matrix is a diagonal matrix, so this is a diagonal matrix because if you were to look at this matrix, the only non-zero elements are on the diagonal. And actually, when you have a diagonal matrix, if you just take the product of your elements on the diagonal, like in this case, 1 times 1 times 1, you're going to get your determinant. But let's say we don't know the trick. Let's fake it. Okay, let's say we want to compute it from scratch. So I rewrite my first column, 1, 0, 0, and then my second column, 0, 1, 0. And now I draw all my arrows. I'm going to start with the plus arrows. So 1 times 1 times 1, plus 0 times 0 times 0, plus 0 times 0 times 0. You can see here, again, I'm overdoing it. Every time you cross a 0, you should just go plus 0, but just to show you where all the numbers are going, I'm going through my 3 arrows and writing all the entries corresponding to those 3 green arrows, and I'm even taking the time to draw them in red. And then again for the anti-diagonals, so if you draw the first one, you get 0 times 1 times 0. The next one is 1 times 0 times 0, and then 0 times 0 times 1. You can see that all these are going to be multiplied by 0. So if you're comfortable, you just go minus 0, minus 0, minus 0. But if you want to see everything when you're learning it, so the first red arrow corresponds to minus 0, 1 times 0, minus again, second red arrow, 1, 0, 0, and then minus the last red arrow, 0 times 0 times 1. And this adds up nicely to a clean 1. That's my determinant for my identity matrix. And actually, in general, IN, so I1, I2, I3, I4, if you learn about determinants for bigger matrices, you will always get 1. And again, no surprise, the identity matrix is like a number 1, so no big surprise there. All right, I'll do one more example from with all details, and I'll leave it to you to check the last example. So again, for me, when I'm doing these examples of my next matrix C, minus 4, 3, 1, 2 minus 2, 0, and 1 minus 6, 0. So I'm going to write, again, my first two columns. So the first one is minus 4, 2, 1. And then my second column is 3, minus 2, minus 6. Time to draw some arrows. So minus 4 times 2 times 0 plus 3 times 0 times 1 plus 1 times minus 6 plus 1 times 2 times minus 6. Again, here, if you're comfortable, do it. Okay, so you should just write 0 right away because minus 4 times minus 2 times 0 is 0. I'm writing everything down just because I have nothing else to do. Okay, but when you're doing it, as soon as your arrow touches a 0, skip it. Okay, so here you get 0 plus the next arrow is touching a 0, so plus 0. Again, I'm writing it just to be annoying. And then the last green arrow, this green arrow, blonde hair, strong guy. Anyway, so plus 1 times 2 times minus 6. And now if I do my red arrows, so the first one is 1 times, hello, 1 times minus 2. Ah, stupid technology. 1 times minus 2 times 1 minus, so I will minus everything here, minus 4 times 0 times 6. Of course, I'm touching a 0. That's a clean 0. And then minus 3 times 2 times 0, touching a 0. There's only one non-zero entry here. So technically, this is the only number you should be writing down. Minus 1 times minus 2 times 1 minus 0 minus 0. But here, just to show you all the computation behind these arrows, I'm writing them, but this is a waste of time. I'm just keeping you busy with me because you're my best friends now. Okay, so here we go. And then if you do the computation, so essentially just by keeping, if you did it carefully, you should just get your minus 6 here, and then you're subtracting, sorry, you're minus 12, and you're subtracting that minus, that minus 2, so or plus 2, you can double check that this gives you a nice clean minus, minus, minus 10. And that's the determinant for that one. And as an exercise, you can do the last one. But here, for the D matrix, make sure you do it on your own. Make sure you double check your stuff. It's very, very easy to make a mistake here. So you want to make sure you are good at this, but you will be good at this by doing this computation quickly but carefully. But I just want to talk about that example again because of that special row here with two zeros. I only got two triplets in my big fat formula that were not zero. And actually, when you have a matrix with a lot of zeros, it makes these computation always easier. So my next remark in my next example is an example that you can worry or not about it. But me, because I'm actually bad at drawing arrows and I will make sign mistakes all the time, I like to use elimination in order to introduce zero. So one very important property that I've just listed here as a remark is that if you do elimination, so if you do operations on the row or even on the column, it actually does not matter. But normally you're more used to do elimination on rows because you've seen the infamous Gauss-Jordan elimination algorithm. So if you are doing elimination on some rows and you're introducing zeros, these eliminations will not change the value of your determinant. And then if you're introducing a lot of zeros in your matrix, you're going to be simplifying your computation. Again, is it easier just to do it? That's kind of a personal question. I would say typically most people for 3 by 3, they just write down the extra two columns and they draw the 6 arrows and they're just careful. Me, I like to introduce zeros in order to do the question. So let's look at the next example, and I will try to convince you that this is an easier way to compute the determinant by using elimination. But again, just take this next example as a tip that you can use or not. So if this is just confusing you, just use what we've seen before. It's not too difficult. Two more columns, arrows on the 3 diagonals minus all the arrows on the anti-diagonal. But here what I've decided to do, because that's me, I decided to do some elimination. Ideally, when you're using that trick, using elimination to create zeros in your matrix, it'd be nice if your matrix had a 1 or a -1, but in this case, we don't have a 1 or a -1. But because we're geniuses, we're going to first create a 1 using elimination. So here, there's many different ways you can do this. This is not a unique path, but you will always end up with the same answer. So for me, I see a 5 and a 4. The difference between a 5 and a 4 is a 1. So by using the following elimination, by saying row 3 is row 3 minus row 1, 5 minus 4 is equal to 1, yes, that's going to be my eliminator. But of course, I do my operation on the full row. So 2 minus 3, that's minus 1. And then for the last entry, if you do 8 minus 6, you get your 14. Now I have a 1. It's already circled in red, ready for action here. So I'm going to do 2 elimination now to destroy the 4 and the minus 2. I want a lot of zeros. The more zeros that I have, the easier it's going to be for me. So I can do row 1 becomes row 1 minus 4 times row 3, and row 2, if I want to destroy the 2 here, I can say it's row 2 plus 2 times row 3. So I'm using that one to get rid of those two entries. Of course, you need to do the operation on the full row. 4 minus 4 times 1, that's 0, of course. 3 minus 3 times minus 1, that's going to be plus 3, so 7. And minus 6 minus 4 times 14, that's going to give you a nice minus 62. And then minus 2 plus 2 times 1, yes, it's going to be 0. 7 plus 2 times minus 1, that's a 5. And 5 plus 2 times 14, that's going to give you 33. And now what you can do is, with that column full of zeros, now you can start rewriting all the numbers. So if you rewrite your first column, so 0, 0, 1, 7, 5 minus 1. You can start drawing your arrows. So I'll start with the green arrows. So you get 0 times 5 times 14, that's 0. And then plus 7 times 33 times 1. So that one I'm going to write down. So I'm just going to do the one that gives me a non-zero. So 7 times 33 times 1. And then plus the last green arrow is minus 62 times 0 times minus 1. That's a 0. I'm not rewriting that one. And then finally, the green arrows, the red arrows in the other direction, minus 62, 5, and 1. That's going to give you a number. So I'm going to write that one. So minus 62, 5, and 1. But all the other red arrows are going to be meeting numbers that are 0. So you're going to get minus 0, minus 0. And if you do the actual computation, you can double check that this gives you a nice 500, a nice 541. So again, if you find that this trick is too much information, if you just prefer to do it using the regular use 2 extra column and apply the formula, good for you. Do whatever you want to do as long as you get to the right answer correctly. So if you like that trick, if you like to use elimination, do it. If not, just apply the formula. Me, I'm a big elimination guy. I would say this one, it's debatable if this was easier or worse. But anyways, it's a trick. Use it if you want to. For that section on computing determinants of 3 by 3, that's it. That's all. Bye-bye.